Welcome back to another Marcus Maths video. Today we're going over quiz 2 in Unit 2 differentiation. Today we're going to be doing a lot more actual calculus, as we are actually going to be learning about the product rule and the quotient rule, that are really important differentiation rules as we start to get a little bit more complex with our calculations today. So quite a bit of prior background knowledge is required for this lesson, but I'll try to break it down and try to introduce us to each of the topics the best that I can. Make sure to like and subscribe if you haven't already as we continue with this AP Calculus BC review. And let's go ahead and get started. So we're trying to find the derivative of negative 7x plus 12 using these differentiation rules. What I would do, just solve it by yourself and then compare what you do with what this Maya person is trying to do. So of course, first we're going to have to split to two separate derivatives. This is just way more efficient this way. It's just the sum rule of derivatives. We can just split them. That the derivative of negative 7x plus 12 is the same as the derivative of negative 7x plus the derivative, or d over dx, of 12. And now from here, we know the constant rule. The derivative of any constant is equal to 0. So the second half is just equal to 0. And then the derivative of any monomial term with a degree of 1, the variable is just going to get cancelled out. Because how this works, we use the power rule. We think of the exponent. We multiply the exponent with the coefficient. Negative 7 times 1 is negative 7. Then we subtract 1 from the exponent. 1 minus 1 is 0. X to the power 0 is 1. So the x cancels out. We simply left with negative 7. And that is the correct answer here. So we would just be left with negative 7 as our derivative. Now notice step 1 is correct. We separate into two different. Step 2 is correct using the constant rule. And then step 3 is where we make a mistake. We cannot split two that are multiplying. We can split two that are adding right here, but we cannot split two that are multiplying. So step 3 is where Maya made the mistake here. Okay, on to question number 2. Just another notation for differentiation when we have an apostrophe here just means we're trying to find the derivative of h of x. We're just going to use that power rule that I mentioned again. We take our exponent and we multiply with the coefficient. 1 times 8 is 8, so our new coefficient is 8. Then we have x, and then we subtract 1 from our exponent. 8 minus 1 is 7. So the derivative of x to the power of 8 is 8x to the power of 7. Okay. On to the next, we're going to be using more derivative rules here. We're going to find the derivative of 4 times g of x plus the derivative of h of x minus 8 at x is equal to negative 2. X is equal to negative 2 is kind of irrelevant because all of these are at x is equal to negative 2. We're going to be using these derivatives entirely. We're not going to be using the regular functions because as we split them, just like Maya did in the previous question, first of all, the constant is just going to be equal to 0. We can eliminate that. And then we split, so d over dx of 4g of x, and then plus d over dx of h of x. If you guys didn't know already, d over dx of h of x is the same as the derivative of h of x, notated like that, at x is equal to 2. So the derivative of h at negative 2. So it will be notated like h apostrophe of negative 2. And then this 4, that's multiplying, we can just move it out here. So we're going to find the derivative of g of x at x is equal to negative 2. Then we're just going to multiply that answer by 4. So we're going to take negative 5, multiply it with the 4 to get negative 20. And then we are going to take the derivative of h of x at x is equal to negative 2, which is 7. And we're going to add those together. Negative 20 plus 7 is negative 13. So that is the evaluation for this a little bit more complex derivative. Once again, we simply use power rule. First, I'll find the derivative, and then I'll substitute in x is equal to 2 for our derivative. So we're going to use that power rule that I mentioned. We move this to our coefficient. We multiply with the coefficient, actually. So our new coefficient, 1 times negative 2, is equal to negative 2. So we have negative 2, x to the power of negative 2 minus 1, my bad. We're going to be subtracting 1 to each of these. Negative 2 minus 1 is negative 3. So we have negative 2x to the power of negative 3, which is also equal to negative 2 over x to the power of positive 3. This is where we're going to substitute in our x is equal to 2. We have negative 2 is equal to x to the power, is equal to 2 to the power of 3. We can notate that like this. 2 to the power of 3. 2 to the power of 3 is 8. Negative 2 over 8 simplifies to negative 1 over 4. So the f of the derivative of 2 is negative 1/4. Okay, on to the next. We're going to rewrite the square root here as a fractional exponent. Remember, the index is 2, so we can rewrite the square root of x to the power of 3 as x to the power of 3 over 2. And then we're going to just apply the power rule. We're going to move this to the front. So we have 3 over 2x, and then we're going to subtract 1, which is x to the power 1/2, meaning we have 3 over 2 times the square root of x. We're going to substitute in 16 now. And square root of 16 is equal to 4. 4 times 3 over 2 is equal to 6. So the derivative of f of x at x is equal to 16 is 6. And remember, derivatives always stand for slope. Okay, multiple steps here. I recommend we just take it one step at a time. Of course, when we're adding, we can just separate into 1 derivative, 2 derivative, and then 3 derivative. First of all, we know that the derivative of x is just going to be equal to 1. We saw that in the previous question. Now let's rewrite these with the negative exponent. So 1 over x to the power of 2 is equal to x to the power of negative 2. And then 1 over x is equal to x to the power of negative 1. And then we're going to apply the power rule to both of these. So x to the power of negative 2, we're going to have negative 2, x to the power of negative 3. Then we're going to have negative 1, x to the power of negative 2. And then we will rewrite these as negative 2 over x to the power of 3. And then negative 1 or minus 1 over x to the power of 2. So our full derivative of h of x is equal to negative 2 over x to the power of 3, and then minus 1 over x to the power of 2, and then plus 1. And that is the correct answer for this one. Write an equation of the line tangent to the graph of g of x at the point where x is equal to 3. So remember, we wrote an equation beforehand. These are all going to be in point slope form. So y minus y1 is equal to m, which is going to be our derivative, x minus x1. First, we know that x1 is equal to 3. We're going to substitute in 3 to our regular equation to find what y1 is going to be equal to. 3 squared is 9. 27 is our first term, minus 45. 27 minus 45 is negative 18. So we're going to have y plus 18 equals m, which we will find very soon, x minus 3. Now from here, to find the m, we're going to take the derivative of g of x. We're going to use the power rule, bring down the 2, multiply with the coefficient. We have 6x, because 2 minus 1 is 1, and then minus 15. And then we're going to substitute in 3 to find what is the derivative, what is the slope of the function at that point. 3 times 6 is 18, minus 15 is 3, so m is equal to 3. So the equation of the line tangent to the graph of g of x at the point where x is equal to 3 is y plus 18 equals 3, parentheses x minus 3. Okay, last question here. So we actually didn't go over product rule and quotient rule. I assume that's going to be tomorrow then. We're going to do power rule, and then we know how this is going to work. Power rule, but we know that negative 7x, the derivative of negative 7x is simply equal to negative 7. And we know that the derivative of a constant is equal to 0. So power rule to x squared is equal to 2x. So we are left with 2x minus 7, and that's it for our first step of derivatives. We're going to be looking into a lot more difficult stuff in the future, but this, consider it the basic differentiation rules. We're going to be expanding on this kind of stuff a lot, but it's really important to just rewrite into exponent and use our really easy to use power rule from there. I'll see you guys tomorrow for our more complex differentiation, and goodbye.